Hello. Today we are talking about a rule for taking a derivative, and that rule is called the power rule. So what this means is if I have a function and I want to take the derivative, will be one of my methods. So we're going to start with terminology. And if we have a function, y is equal to f of x, we can represent the derivative in several ways. In other words, you can be asked to find the derivative several ways. This is the first notation that we have for derivative, and that is read as f prime of x. So f is my function, the prime means that's your derivative, and the function is in terms of x. The second way we can ask for a derivative, or you can represent a derivative, is in this notation. And when you read that, you would say y prime. The next notation we have is dy dx, which looks a lot like the change in y over the change in x. And I'm going to write just a little bit more about that. That would be something like y2 minus y1 over x2 minus x1. And that looks a lot like slope, which is a rate of change, which actually is a derivative. So that's what this circled notation means. And then when I say it, I say dy dx. Yes, that's not what it says. It's really dy over dx, but we call it dy dx. The fourth notation, this is actually not a thing. Everything that we've done so far will end up being a function. These are all derivative functions. This one's more like a command. So in this one in number 4, this notation means take the derivative of y. I'm going to write that down even though that's not what it says. Take the derivative of y. When reading that, you would say d dx of y. And this is, again, an operation. This is something that you do. So now we're going to move on with our lesson. And what you're going to do is I'm actually going to do all of the work for these problems right here. And then you're going to write down the result so that we can find a pattern. So again, all you're doing is you're going to be watching me work these problems. So we are going to find the derivative of this function, and we're going to use the definition of derivatives. The first thing I'm going to do is I'm just going to plug in my function. Now, in this problem, when I plug in x plus h in for x, I get x plus h, and then I subtract f of x, and f of x again is just x, and I have that all over h. And all I'm going to do now is some simplifying, and again, you're just watching, you do not need to write this down. On the top, I have just an h left because my x and my negative x go to 0. And now I have this limit as h approaches 0 of h over h. And h over h is just a silly version of the number 1. And now that I'm taking the limit of a constant, that limit is just 1. So in our pattern, what we have is if f of x is equal to x, f prime of x is equal to 1. So that should be written down on your paper. And now we're going to move to the next one. So now we have the function f of x is equal to x squared. And again, we're going to do the same thing. So f prime of x is still going to be a limit. And I'm going to plug in x plus h into my function, which means my x plus h is going to be squared. Then I'm going to subtract my f of x, which is just x squared. And this is all over h. So at this point, I just have some algebra to do. And when I square out x plus h, I'm going to go ahead and write that out just so everybody knows exactly what I'm doing. I'm squaring that out. And now I'm going to multiply that all out, which means I'll end up with 4 terms. And then here I can do a little bit of simplifying. I know that these are going to give me a total of 2xh. And I also know that I have a negative x squared here and a positive x squared. So those are going to be 0. So simplifying this, I now have 2xh, and then I have plus h squared, and that is all over h. So at this point, what I really want to do is I want to get rid of this h in the denominator if I possibly can. And I actually can. So on the top, can I factor by GCF and factor an h out of there? And I can. So take my limit still as h approaches 0. I'm going to factor out an h, and I'm left with 2x plus h. And again, I see I have a silly version of the number 1. That's just the number 1. So I simplify this a little bit more, and I end up with 2x plus h. And now that h is 0, I can plug 0 in for h because I don't have a 0 in my denominator anymore. And that leaves me with just 2x. So now I know f prime of x is 2x. And you can write that down on your paper. And then we'll move on to the next one. So now we are doing the derivative of x cubed. And again, I'm using the definition of derivative to find that. So my derivative is going to be the limit as h approaches 0. I'm now going to plug x plus h in for x, which means x plus h is being cubed. And I'm subtracting f of x, and f of x is x cubed. Now I'm going to do a little bit of algebra here just to kind of show you what I'm doing. And I'm basically going to take x plus h times x plus h times x plus h, and then I'm going to subtract x cubed. But I've got to do a lot of algebra to kind of work out that x plus h cubed. So I'm going to multiply the first two together. And when I multiply the first two together, I get what I got the last time, and when I had simplified it, I ended up with this. But I still need to multiply that by an x plus h. And now what I need to do is I need to multiply the red x squared plus 2xh plus h squared times the blue x plus h. And when I do that, I'm going to get an x cubed plus x squared h plus 2x squared h plus 2xh squared plus h squared x, but I'm going to write it as xh squared, and then plus h cubed. And now I need to simplify what I can. And when I simplify what I can put these two together for a total of 3x squared h. And I can also put, let's see, these two together, and that gives me a 3xh squared. And then I have everything else still, x cubed plus h cubed minus x cubed. And I did not catch what I just wrote down, which is I have an x cubed up front, and I have a subtract x cubed at the end, and those, of course, simplify to 0. So let's write that out one more time. So now I have 3x squared h plus 3xh squared plus h cubed all over h. And again, just like I did before, I'm going to look for a GCF, and I have a GCF on the top. The GCF I want to have is an H, and I think I've got one. I've got an H here, I've got an H here, and I've got an H here. So let's do a GCF, factor by GCF. Sorry, jumped there. And I pull an H out, and I'm left with 3x squared plus 3xh plus h squared all over h. And I found a silly version of the number 1, which means I don't need to write it anymore. And now I'm left with 3x squared plus 3xh plus h squared. And again, h is approaching 0. So this is approaching 0, and this is approaching 0, which means I'm left with 3x squared. So if I start with f of x is equal to x cubed, f prime of x is equal to 3x squared. Make sure you have that written on your paper. I'm going to go back to our paper now. So written on our paper, we know that the derivative of f of x is equal to x is 1. The derivative of x squared is 2x. And finally, the derivative of x cubed is 3x squared. So what I'd like you to do is see if you can figure out what the pattern is, and then I'd like you to make an educated guess on the derivative of x to the 10th. So please pause the video here to fill in the box. Really pause the video, write it down, write something down. You've got to have some idea of a pattern. So I'm going to start actually with the bottom part to see if you got this part correct. And this derivative is 10x to the 9th. And hopefully that clarifies the pattern. But the pattern is, if I have a function is x raised to an exponent, then the derivative is going to be n times x raised to the exponent minus 1. That is your power rule, and that we need to memorize. These derivatives will be used all year long. It's not a difficult rule. You'll get used to using it. So let's talk about a couple additional rules about the derivative. The derivative of a constant. So if I were to have a graph and I had a function, we had a constant part. Here's your constant part right here. And what is the slope of that, or the rate of change of that, or the derivative of that? And that slope is 0, and that rate of change is 0, and that derivative is 0. And again, this is saying d dx of c is equal to 0. So down here we have a few to do. If you would go ahead and write down the answers to these two. So each of these are constants, so the derivative of 3 is 0, and the derivative of negative 7 is also 0. Second rule that we have with derivatives. This is our actual power rule. And again, I wrote that down up above. So that is, you bring the exponent down. Your variable is now raised to the exponent that it was, but you subtract 1. So I would like for you to go ahead and do these down here. So for the first one, I bring the exponent down. X is now raised to 10 minus 1, which is 9. In the second one, I bring the exponent down. T is now raised to 3 minus 1, which is 2. And that should compare exactly with what we did earlier. Moving to the next page. We have a couple more. And you're going to treat these exactly the same, so don't get worried about anything. This first example right here, this derivative, theta is a variable, so I bring my exponent down. Theta is now raised to 5 minus 1, which is 4. In the next example, you do the exact same thing. Can you try this one? I want you to do this one, please. In this one, I bring my exponent down, which is negative 4, and x is going to be raised to negative 4 minus 1. And that, negative 4 minus 1, is negative 5. So just be careful with your negatives. A lot of people like to try and add 1 to that instead of subtracting. Now, the next one, this doesn't look like it's a power rule at all. I don't even have an exponent. So if I'm in this situation, I always try and rewrite. So right now what I have is y is equal to 1 over x. Can I write that as x raised to a power? And I can. The power of the x in the denominator right now is a 1. It's really x to the first power, and it's in the denominator, which means its exponent is actually negative. So we rewrite first. Once we do that, we should be able to write the derivative, and that would be, I'm going to write it next to it, where I prime is going to be, I bring my exponent down, x is now raised to the exponent subtract 1, so that's going to be a negative x raised to the negative 2. Now, because the form of the original equation was 1 over x, I should probably translate this into that form. So the negative will stay on the top, and my x squared, because my exponent is negative, tells me to move this entire thing to the denominator. So this derivative is 1 over x squared, and it is negative. So I would like for you to try this one. So for this one, I bring the exponent down, and x is raised to that exponent, subtract a 1. And that's not a very friendly one, so let's make a friendly one. And the friendly one's going to be the fraction, which would be 4 over 4. So 3 over 4 minus 4 over 4 ends up being x raised to the negative 1 over 4. And because that's the form that we originally started, you can leave your answer like that. In the next one, we have another one that we need to rewrite. Again, there's no exponent here, so I definitely need to rewrite it. So how do I rewrite this as an exponent? F of x, if I had the square root of x, is the same as x raised to the 1/2. At this point, I should be able to take the derivative now. I bring my exponent down in front. X is now raised to the 1/2 minus 1. I'm going to change my 1 to a friendly 1, and that's going to be 1 over 2 minus 2 over 2. And 1 over 2 minus 2 over 2, I believe, is negative 1 over 2. I should probably put it back in the form that I was in, which was in radical form. So I have two things going on. I have the negative sign, which tells me to move this thing to the bottom. And then I have the 1/2, which tells me I really have a square root. So this one I would leave as 1 over 2 square root x. We have another rule down here, rule number 3, and this is the constant multiple rule. So if f is a differentiable function, all that means is I can find its derivative, and c is a constant, then this means take the derivative of some number. The c is just some number times a function. Then when I find its derivative, I'm going to have that same number times the derivative of the function. So that constant in front is going to stay along for the ride, so to speak. So looking at this, for the first example, my 3 is going to stay, and then I'm going to take the derivative of x to the 4th. And x to the 4th derivative is 4x to the 4 minus 1, which is 3. Then all we do is simplify that, and the 3 times 4 is 12. Can you go ahead and try these 3, please? Please pause your video and complete those 3. Here are the answers. So if you have any that are incorrect, please pause the video to see if you can try and fix your mistakes. If you cannot, please write down questions that you have about these examples. I'm moving on to number 4. Rule number 4, the sum and difference rule, which is quite simple. All of these words up here just mean everything we can take the derivative of. And all this is saying is if I have one function plus another function or minus another function, how do I deal with that? And you deal with it simply by taking the derivative of the first function and you add or subtract, however the problem was originally stated, the second function. That's it. So when we move on to this next example, we have all of these different monomials put together to make our large polynomial. You just take the derivative of each thing. So the derivative of 3x to the 5th is 3 times 5x to the 4th. My next term is minus, my 2 stays, the derivative of x to the 4th is 4x to the 3rd. Next, I have a 9x, and that derivative is just 9y. Think about it, think about it. Okay, and then the last one is -1, which is a constant, and the derivative of a constant is 0. And then all I would like to do is simplify this. And so the first term is 3 times 5, which is 15, x to the 4th. 2 times 4 minus 8x cubed plus 9, and that is the derivative. I would like for you to try this next one, so please pause the video and complete that last example. Here is the answer to that last example. If you got that correct, continue with the video. If yours is not right, please pause the video here to work on fixing what you have. Next page. Second and higher order derivatives. So all this is let's talk about what all these different notations could possibly mean. So y prime equals dy dx. That means the first derivative of y with respect to x. Take the derivative. That's all that means. Derivative. This next one has these 2's in here. And what that means is the second derivative. So what that means is you take the derivative and you get a function. Then you take the derivative again. So many people, although I'm going to call this the second derivative because that's what it's called, many people call this one the double derivative because you're taking the derivative twice. The next one is the third derivative, which means you're going to take the derivative 3 times. And this notation just means the nth derivative, which means you're going to take the derivative n times. So for this one, in this example, I'm going to slide down just a little bit. Take the first 4 derivatives of y prime. So I'm going to start by taking, sorry, of y. Y prime is my first derivative, so that's going to be 2 times 3x squared minus 4 times 2x plus 3. And that's going to simplify to 6x squared minus 8x plus 3. Now I'm going to take the second derivative. I'm going to write it as y double prime. So I come to my 6x squared, and that is 6 times 2x minus 8x minus 8, and then the plus 3, that derivative is 0. And I simplify that to 12x minus 8. Then I take the third derivative. The derivative of 12x is just 12. The derivative of 8 is 0, so that gives me 12. And then I take the fourth derivative, and that's a constant, so that derivative is 0. For this last bit, we are looking at derivatives numerically. So we've been, sorry, I'm going to slide a little bit. We've been given some information. Sorry. We've been given some information, and we're going to find these derivatives. Sorry for my screen confusion there. So let's look at this example. Sorry, I have all these numbers up here, and I'm going to reference these kind of as we go. For all of these, we're finding f prime of 3. So first thing I need to do is find f prime. So f prime, again, using my sum and difference rules, I can just find the derivative of g plus the derivative of h. And now I want that at a specific x value. I wanted it at f prime of 3. So I'm going to plug in 3. And now I'm going to reference the information I was given at the top. And the information I was given at the top should help me to figure this all out. So g prime of 3 is the first thing that I'm looking for. G prime of 3, and I look up and I find g prime of 3 is 10. So that's going to be 10 plus, now I'm looking for h prime of 3. H prime of 3 is negative 2. And then I simplify that, and that leaves me with 8. For the next example, we're doing the same sort of thing. So first I find f prime of x, and this is going to be a constant stays there times the derivative of h plus my constant in front stays times the derivative of g, and the derivative of a constant is 0. Now I need to use the information up above. So I have, I'm sorry, I'm going to plug in my 3, then I'm going to actually look for my information above. 5h prime of 3 plus 3g prime of 3, and I don't need my 0 anymore. H prime of 3 we knew was negative 2, so now I have 5 times negative 2. And then I need a g prime of 3, and g prime of 3 was 10. So I have plus 3 times 10, and I can simplify this to negative 10 plus 30, and that simplifies to 20. So I would like for you to try these two. Please pause the video here and complete these two examples. My answers are circled for each of those. The first one I got 22, and the second one I got 7. If you did not get those, please look over your work and my work and write down any questions and bring those to class. Have a wonderful day.